Hi everyone, welcome to Omics Academy. So today we are going to say how we can generate a heat map or violin plot to see the demethylation pattern across the genic region. So let's imagine you have a set of genes, and these genes the length of the genes are probably different. Some of them are short, some of them are longer, and we may have thousands of genes like this. And now you want to say, okay, if you have a whole genome bisulfite sequence data, you want to know the demethylation pattern across the genes, and how will you use the data visualization skills to visualize this kind of data set. So here we are. First, I'm going to show you one example. People use ChIP-seq data. So here the Perl2 ChIP-seq data to show you the Perl2 values. So across the genic region. For example, this is the transcription start site, transcription end site, and we can see that the Perl2 are kind of enriched in this transcription start site. So how to interpret this data? So this figure, let's say this is the figure legend, the color code. So as we can see here, the higher the value we have, the bluer we will observe here. So as you can see here, we see lots of bluish color here around the TS, a little bit downstream of transcription start site. So this kind of heat map can help us to understand, let's say for ChIP-seq data, where the proteins are binding to on the genome or on the genes. And similarly, for when we have whole genome bisulfite sequence data, we'd like to see what's the patterns across the genic region. So today we are focused on the genic region. We are not going to focus on the upstream and downstream region. Let's only focus on the genic region. So just to make the problem easier to understand. So let's first talk about the strategy, how we are going to finish this task. Okay, so again we have let's say thousands of genes, and how we can generate a heat map like what we just saw using the ChIP-seq data. So first we have the input data like the gene coordinates, and then we will have the demethylation data. So I will show you later about the demethylation data. And so we have the two input files, and then the output file should be something like this. Let's say let's insert a table. Okay. So let's say we have a gene 1, and because you can see here the different genes have different lengths. So what we can do is we can split the genes into let's say 20 beans. Let's say not by the bean length may also vary from gene to gene, but for each gene we have a specific number of beans. For example, let's say 20. Okay, so we will have bean 1, bean 2, until bin 20, and then this is the bin 19. So for each gene, we'll have a corresponding methylation value for each of the bins. For example, we have gene 1 until gene N. Okay, so this is the input file. So the first one, this is the input file 1, which is the gene coordinate, and then the input file 2 will be the demethylation information. So for the demethylation information, we will have something like this. We'll have something like this. For example, the first column is the chromosome ID. The second column is the position on the corresponding chromosome, and then the strand. So on which strand we have this cytosine, and then we have the C number, the cytosine number at this position, and the T number. Basically, for the reads mapped to this this particular location, what's the number of C's and what's the number of T's. So if you are not familiar with this, go to check Bismarck manual. So, and you need to have a fully understanding of whole genome bisulfite sequencing data. Okay, and then the 1, 2, 3, 4, 5, 6. The sixth column is the context, the cytosine context. So here we only outputted the CG context, and we don't really need to have the last column in this for this task. Okay, so here the the input file 2 is basically the demethylation information. Okay, so how we are going to achieve this? Okay, so here we have a set of let's say we already have this ENV, the whole genome bisulfite sequencing for this sample EV1. So EV means empty vector. Basically, it's a yeast strain with a transgenic of empty vector. So here we also have other samples. For example, we have a transgenic strain with DNMT3B. DNMT3B, as you know that DNMT3B, the D-methyl transferase gene, and so we are going to copy this gene also. So basically, we are going to compare the demethylation for these two strains. So one is the empty vector strain, and one is the DNMT3B transgenic strain. So let's say how we can do this. So to do this, as you can imagine that on the genome, for example, in yeast, it's a relatively small genome. But if you think of the genome like human genome or mouse genome or even plant genome, usually it's very big, and there will be lots of cytosines, even CG cytosines. In CG context, there will be lots of sites, and which will lead, we have a file with millions of rows. So for that, if you want to extract, for example, for particular genes, for this gene, if you want to extract the demethylation for this particular gene, you might, if you just need to go through the file like line by line, it will consume lots of time. But another strategy, you can read the file into the memory, but that will consume lots of memory. For lots of the cases that your computer won't afford such amount of memory. So what we usually do is we use this there's the Perl. If we use Perl to accomplish this task, there's the Perl package called biodbhtst-tabix. So basically, this provide us an access to the underlying TBXC method. So, in briefly speaking, it's just let you to quickly and easily, access the demethylation data without consuming lots of memories. That is the purpose of the advantage of this package. Basically, if you have a gzipped file, and then you can query the information with this format. So basically, you can first create a variable called TBIX using this new function, and then you can use query function to extract the information that within this genomic coordinates. And then you can use, once you have this new variable called, let's say here, it's named as $ITER, then you can use this variable, use the function next to get the rows like one by one. Okay, so this is very straightforward. So I will show you how to use this to accomplish our task. So first thing we need, let's write this script to accomplish this task. So let's say we write a script called mass heatmap. So we first write the shebang line, and so what we need, the input file we need is the coordinates, and then the methylation information, and okay, this will be get from the parameters. So based on the information here, so we can just copy the example code into our script. So we need to use this package, and then we need to create this variable. So here, instead of within this specific file, we are going to use our input file, which is this one, this methylation information, right? Okay, so here what we need to do is we need to for each coordinates in this file, we need to get the methylation level for each of the bin. So where we just mentioned here. So we need to go through each of these coordinates, which is a file like this. We already have the file here. Let's say we already have the file here. So here the file, the input file, the gene coordinates here. So let's just copy a few lines into the flow chart. Okay, so Now we need to, for example, for this gene, we need to extract the information from this file to extract the rows within these coordinates. Okay, so let's see how we can do this. Okay, let's go back to our script. So now what we need to do is we need to open this coordinate file. Let's say we use a file handle name COOR with all uppercase letters. And then for each of the rows we need to process the file. Let's say we have we need to get to the coordinates first. CHR start end and the ID and the strand. So here strand is also very important because for 5' and 3' we might have different patterns. So here it's important to record the strand information. So basically here from bin 1 to bin 20, we mostly we mean here bin 1 means the 5', the first bin on the 5' and bin 20 means the last bin on the 3' end. Okay, so we need to keep this in mind. So that's the reason we need the strand information. So here we just need to split. So and now what we can do is we can extract the rows within this coordinate. Okay, so what we can do is we can use iter equals. We just copy this information, this example code here. We just change the coordinates here. Instead of using this coordinate, we are going to use this specific coordinate. And now basically we already extract the information. So what we need to do now is we need to get the bin information. So basically what we need to do is we need to let's say we need to assign each of the rows to a specific bin. So we already know we have 20 bins. So how can we get to the 20 bins? Let's say if we want to get the bins, we first need to get the bin size for each gene. So for example, for each of the loops, we need to get the bin size. Let's say the bin size. Let's say here we already set the bin number. Let's say the bin number we can provide from the parameter. Let's say bin number, and as by default we just call it here. We just assign a bin number equals 21st. That makes things easier. So here we just say okay, the bin size equals the end minus stt, which is start, and plus 1, and then minus and then divided by the bin number. Okay, so now we got the bin size, and then we can judge for each of the rows we extracted from methylation information. We can judge which bin a particular cytosine, a particular position belong to. Okay, so let's say we have So let's get each of the rows from this region. From this region. Let's say while this line equals this iter equals next. Okay, so now what we can do is we can we have the rows. We have a row in the methylation information. So we then need to extract the information for each of the columns. So we already checked the files. We know that the meaning for each column. So the CHR, the chromosome ID, partitions, the strand information, the number of Cs, number of Ts, and the context. And then what we need to do is we need to say what's the which bin we should assign this partition. So then what we can do this based on this partition. So now we need to use the strand information, because let's imagine we have a gene. If the strand is plus, we have the gene goes like this, and if we have a minus, the gene goes like this. And when we have a gene like this, if let's say we have a partition here, we can use this partition minus the start, and then compare to the bin side to judge to get the bin number. And otherwise, if we have a strand like this, we can use this partition minus the end side here, and then use, for example, we have a partition here, and then we use this partition to minus this end side, and then use this length, divide this bin side, and then get the bin number. Okay, so let's say if this strand equals plus, what we need to do is we need to this is the start, this is end, right? This is the start, this is end. So let's say else means this. Okay, now we can say the bin equals this partition minus this start and plus 1 and divided by the bin size. So this will help us to get which bin this particular cytosine belong to. And similarly, for here, what we can do is the bin here we can use. Let's say we can initialize a bin variable like this, and here we don't need this my anymore. So bin equals position, and here we need to use the end side and plus 1 and then the bin side. So one thing we need to be careful here is the bin number should be an integer. So, and we might encounter the float number after the division here. So here we need to specify this. We need to convert. We need to make sure that this is an integer. Okay, we need to say, okay, this is integer. Can just do it like this. And another thing that we don't, so this division may also result in the value below 1. So, and it's depending on your choice. So, it might be like if you want the start prediction, the start bin to be bin 0, you can just leave it like this. But if you want to have the start bin size, the start bin number at 1, you can here just say 1. So here we just add 1 here just to make sure once we have this division, if this division resulted in a value below 1, so then we will have a 0 here. And to make sure we start from we start from 1, so we just here we plus 1 here. Okay. So now we have the bin information. So what about the so we need to have something to store the methylation for each bin. So to do this, because we already have the kind of like we have a bin, and we have for each gene we need to have different bins, and for different bins we will have a methylation level. So it's kind of like a structure like this. So we have a gene, and each gene we might have different bins. Bin 1 onto bin N, okay, and then we will have the methylation information. So for such structure, you need to usually think of the a hashi that which can help us to do this. So what we can do is we can do something like this. So let's say record mass information here. We initialize a hashi like this, name that rack mass info. So for each row here we can say, okay, rack mass info, and for the key we use the gene ID, the ID here, and then we know the bin side. Okay, we will have a bin, and then for the methylation level, what we want to do is so here we need to record both the C number and the T number. So here we need to the value will be an array. So here will be have the 0 to be C number, just plus equal C number, and here we have the T number in the second element of the value in the hashi. Okay, so now once we done this, we can print the hashi information. So let's say we have so for each of the case in this hashi, which is the gene ID, right? Which is, let's say, just say ID, and then we say rec mass info and ID, and then because we have a fixed number of fixed size of bins, and here we have 20, so we can say for each, let's say for I equals 1 until I is not larger, is smaller or equal than bin number. And here just plus plus. So now we have for each gene we have a mass array to store the information for each bin. So let's say we just initialize 1, and then one thing we didn't mention so it's possible that for a particular bin there's no reads covering that bin, so for that case we won't have a value there. Okay, so it's possible that we don't have any information. It's also, so for that case, and another case is we might also encounter the problem that for a particular gene, no reads covering that gene at all. So for that case, it's okay because here we won't. So only the genes have information will be stored in this hashi. So if not, we won't. So basically, that particular gene will be ignored. But for bins, it's possible that even we have the ID at the key in this hashi, but we don't have some of the bins, we don't have the information. So first we need to judge whether there's the information for a particular bin. So let's say here we have 1, 2, 3, 4. If not exist, if we don't have this, if it's not exist this, if the bin there's no key for this bin for this particular gene, we just say 1, 2, 3, 4. We just push cam bin mass. We just push an NA into this array. So, but else, if we have information, we'll just calculate the methylation information. Okay, let's say we have the state number and we have the T number. So the methylation level will be this ID, the I. So here is not bin, here is basically I. And here we will have I and I plus this C number plus C number plus T number is the denominator. Another thing we need to mention so it's possible that even though because for this methylation level, the methylation report, cytosine report, was reported by Bismarck. So it's possible that even there is no information in a particular prediction, the Bismarck will report the corresponding read depths, the C number and T number for that prediction. And all the T, C number and both of them will be 0. So we might also encounter that we have a denominator here at 0. So we need to avoid this. So, but basically, okay, here is the mistake. So here we need to say T number. So here we need to do one more step to check the denominator value. So let's say if, let's say the total depth equals this. Okay, so let's say here we just say total depth. So here we need to do one more step of judgment. So if total depth equals is above 1, 1, 2, 3, 4, and if it's above 1, we'll get the methylation level. If not, basically here we will just have we'll just push an NA to the bin, to the methylation information. So this is one way, but here we can also control the depth here. We can ignore the the prediction that have very low coverage. So here, for example, say next, if these two, the sum of these two numbers is below a specific value, let's say 10. Okay, so this will ignore all the predictions that have read depths below 10. So with that, here we don't even need to use this anymore. Here we can just say, okay, we can remove this, because once we have information, we will have, so all the zero, the prediction don't have any read will be ignored. So here we can just say something like this. Okay, now with that we can output the information here. So let's say we have ID, and then we have the information for each of the bin. Let's say join -t and then -n. Okay, now let's check this script. Let's see whether it will work. So here we don't specifically say bin 20, so we'll just give 20 on the command line. So let's say whether we will encounter any errors here. Seems that we have some errors. So basically here said the rack methylation level requires explicit packaging name. Let's say, oh, here, because we want to use the hash here, but we don't really initialize a hash. So let's try again. So still this ID requires explicit packaging name. So this is 3440 the bin, and again 40 the bin. Okay, let's say 34. So basically here we should use case So basically we want to loop through each of the keys in this hashi. Okay, let's check again. And this bin in 40. Oh, okay, so here the bin is basically not bin. Here we have $i. So all those information may cause the error in our script. So now I think there's nothing wrong, because now the error message or the warning message just because we don't have the corresponding information given here. So let's say we have let's say what information here. So we have coordinate, methylation information, and bin number. Okay. So we have the coordinates information, the methylation information, and the bin number is 20. Okay, let's see what we can get here. So here you can see that we get some output, but all the output shown here is NA. So let's check what happened here. Okay. So first, let's say whether we have information got here. Because if we get everything NA, that means we don't really have any the ID and the bin number at case in the hashi. So let's say what we get, whether we get anything here. So let's say we just say print bin, and then let's say we just print the thing number, this information. Let's see what we got here. Okay, so let's output this into a text file. So basically we got something here, but still we couldn't get any information in the, let's say, this means we have the bin number and the demethylation information, but let's get the end of the information here. Let's say we till the last 100 rows, and basically there's no information. So let's say why this happened. So if we can get information here, let's say what we will get here. Let's just output these two values and the ID information here. Let's see what we get. So first we get some uninitialized value. That makes sense because we just mentioned that for some of these we may not get anything. So think that here we only have this ID and this plus. Okay, let's see what happened here. ID and this plus. So basically there is no information for this value and this value, for this variable and this variable. But here we try to get this to okay. The problem, another problem here we found is so here once we get the methylation level, we need to put it in this array. Let's say we say mass level. And now actually you can see that we have some of the, we still have lots of NAs, but we started to have some information here. Okay, we also need, another thing we need to do is we need to have a header to show the bin numbers. Okay, so here we need to have let's say another array to record the bin number, just to record all the bin numbers we used here. So basically here we will have, once we have the we have this information, we need to record the bin number information also. And that's just plus, we don't even care about the values. Okay, once we have this, we can get the bin number key. So basically this is used as key here. So equals keys. Okay, now we can output the header as this ID and the array and the new line. Okay, let's output this into let's say let's out this mass h and txt. Let's output this into this file. Okay, not this file. We have to give the sample information ev1. So we can just remove this file. Let's see what we have here. Okay, so another question, another problem here is so once in the when we get to the case, the bin number is not sorted based on the bin. Let's say if we want 1, 2, 3, 4, because here we have 1 until 1 to, let's say, bin number here 20. So here we need to sort the bin number based on the values. So let's say A equals, and sort basically from the smallest to the largest. Let's say what we get here using this script. Okay, now we have this bin 1 to bin 20. So also I want to say this is the bin. Here we can just give a bin, give this bin a prefix. Let's say just bin and bin. Okay, here we'll have example that here the bin is not numeric. Okay, this causes a problem. So we will comment out this, and So then for the join, we will join -t, and for the first element, we also need a bin for the first bin. So let's say what we get. Okay, now we have 21 columns and the gene ID. But basically, we see here we have lots of NA. So I don't know whether this is a good way. Whether this is because we have very limited reads, or because of what other things. Let's see. Okay, let's try the other sample, DMT3B. So here we use okay, here let's run this. So now we can see here we have less, much less NAs here. I think the main reason, okay, the main difference between ChIP-seq and whole genome by subsequencing, so the main difference between whole genome by subsequencing and ChIP-seq is, especially for this heatmap generation. In ChIP-seq, it relies on the read density. So even if there's no read, it's fine. That means the read density is very low. But for the whole genome by subsequencing, it relies on the reads and also relies on the cytosine. Basically, it relies on the reads only. So if there's no reads, we couldn't get the methylation level. So basically, if there's no reads, we couldn't have any conclusion. So we couldn't say the demethylation is low or high. But for ChIP-seq, if there's no read, we can say, okay, the signal is low. So okay, let's try to generate the heat map on this file. And since we have NA values here, so for the usually we need to have a heat map package that can deal with this. And I just checked online. I think this package might help us to do this. So let's first install this package. And we are going to use this p heat map here. And so in this p heat map function, it has NA column equals gray. Basically, for all the cells, the NA will be shown as gray. So here there's one more problem we didn't mention. Let's go back to the script. So let's imagine we have a gene with a length 1K and the bin number is 20, and now we will have a bin size of 50. Okay. Now if we got a prediction that is so here if we get a prediction that is exactly at the edge of the prediction, for example, we have the strand is positive and we have exactly at the end of the prediction, then we will have 1000 and divided by here bin size, which is 50, and here equals 20. But here we added one. We add 1 here. So in this specific case, we shouldn't add 1. So here we need to do a little bit adjustment here. So let's say if bin is above bin number. So basically, let's say for this specific case, let's say bin equals 21, and then we need to give a new number. So basically, we need to minus 1 for this bin. So bin equals bin minus 1 here. Okay. The reason we do this is we don't do this in the output. In the output, you can see that in the output, in the header, we will have bin 21. Okay, so this is just to avoid this problem. So you can try the script, trying to comment this line out, and then try to see what result you will have. And you can also kind of think of this specific case and just go through each of the step on a notebook, and then you will be fully understanding this problem. Okay, now let's run this again. Okay, now let's look at the result again. Okay, now we only have 20 bins, and when we look at the columns for each row, and we can see that all the rows have 21 columns. Okay, let's run this, trying to read this file. So let's use heatmap to visualize this result. So first we read this file, and we use the first row as the header and the first column as the row name. And then we can see that here there are lots of NAs. So with NAs we couldn't really do cluster here. So if we want to do if we just want to visualize the whole map data frame, so we need to use this NA color equals gray, and then the cluster row equals false, and the cluster column also equals false. So, and also we usually we want to sort the table, for example, based on the sum up of the rows. For example, so in this specific case, what we want to do is we want to order the table based on the row sums, using row sum and order. Sometimes depending on whether you want to sort the data in a decreasing order or increasing order, so you can set this parameter. For example, you can set this parameter at t. So now we get a new table, and then let's use heatmap library, and then we can generate a heatmap. So here you can see that we don't really see a clear pattern. So and also we couldn't do the cluster. For example, if we use cluster rows equal to true, we will get an error message. One thing we can do is we can remove the rows that are with NA. So we can use this complete case and then we can get the rows that with NAs and without NAs, and then we can generate a new table no NA, and then we use the p heatmap and the p table no NA. So with this, we can clearly see that you know, here the bin 1 basically this TSS transcription start site, and this is the TES transcription end site, and we can clearly say that for majority of the genes we have relatively lower demethylation here, and when we go to the 3' end, we can see that we have a higher demethylation level, and at the end we also tend to have relatively lower, but not as low as the 5' end. So if you look at here, okay, and with this we complete this task. But one thing we need to emphasize again about the NA. So basically, if you use chip-seq data, there's no such issues, because the chip-seq signal is dependent on the read density. But for whole genome by software sequencing, it relies on the methylation information in the read. So if there's no read covering that partition, so we won't be able to get the methylation information. So that's the reason why we have NA, but in chip-seq we won't have this situation. I think that's also the reason usually we use this strategy to process chip-seq data, but not whole genome by software sequencing. So for whole genome by software sequencing, usually we just generate a metaplot, which is the just the average of each bin, and then plot the average of each bin across the gene. So which I can do a Google search and get one example. Let's say metaplot by software sequencing. And we can get an example here. So basically, we still need the same information. Just what we do is we calculate the for each bin we just have one value, and then we can plot these values across the gene model, which is this. But here we don't include the upstream 2K and downstream 2K. So, but you can use similar strategy to do this. We will cover this later in the Perl script. Okay, so let's say one example. So basically, this is an example, but it's a different element, different genomic feature. So here the transportable element. So the same idea, you can divide the transportable element into like a specific number of bins, and then for the upstream and downstream 2KB, you can split the upstream 2KB and downstream 2KB into, let's say, 100 base pair bins or windows, and then for each bin or window you can get an average methylation level, and then you can plot the average methylation level across this model, and then you can use the line to connect each dot, and then it will be forming a line here. Okay, so I will stop here, and also I will include the script link in the description of the video. If you like this channel, please subscribe and like this video. If you want to get notification, please click the bell button after you subscribe this channel. Thank you. Bye.